Welcome to Chatting with Chuck. I'm your host, Chuck. You know, in my previous episode, I mentioned how I had to evacuate, you could say, for a hurricane. And, you know, you have a lot of time to think about things. And even though you're not supposed to think about work or things related to stuff like that when you're on the road, but when you have a lot of time, you do. And you see things, and I notice how the IoT is everywhere. And I thought I'd take this minute to talk about how you can make the IoT work in industrial wireless sensor nodes. It's easy for me to say. So I'm starting thinking about this, and I put a little thing together here. And bear with me. I'll go through this, and hopefully I can help you out or give you some advice, or I don't know. Maybe just find it interesting. So anyway, you know, the Internet of Things, is both a large industrial opportunity and a huge industrial challenge. Applications of the IoT include everything from smart cities to cattle roaming on a range. With distributed facilities like wind farms, pumping stations, and other areas, the ability to gather data from a wide array of devices opens the door up to better monitoring and optimization of performance, and is measured by output, return on investment, or other metrics. However, to achieve the maximum IoT benefit, there must be a dense sensing network, because that is the best way to collect the required data. This leads to multiple challenges: dealing with a variety of equipment and signal types, managing complex communication, deploying expensive transmission cables, handling a harsh environment and tight installation space. These challenges act as barriers to implementing an IoT strategy, but they can be overcome with the right technology. Of particular importance is the communication protocol and scheme, which should be wireless. It also should be capable of cost-effectively meeting the requirement of a wide area, long-distance coverage, but low data rate communications. Such a capability can be combined with flexibility, cloud integration, standard communication protocols, and a rugged implementation to create a solution to the barriers standing in the way IoT deployment. So let's making the most of the IoT. The IoT has generated considerable interest. That is why it's easy to see and why. On one hand, the business opportunity is significant. For instance, the number of connected devices is expected to nearly triple from 2016 to 2021, rising from 17 to 45 billion units worldwide. During that time, IoT software revenue will more than double, climbing from just under $35 to about $80 billion. As a result, there is a ripple effect that is moving through various industries. Some are reacting because they will supply the devices that form the basis of the IoT. For example, the semiconductor industry is looking to the IoT as a key driver for future growth, fueled by the demand for sensor, communication, and processing chips. In other industries, the focus is on IoT applications, with 70% of companies responding to a survey saying that they are either implementing or exploring IoT uses. The list of possible IoT applications includes smart cities, the sensor arrays being deployed, for example, to make traffic counts. Some of these systems are for keeping track of cars, trucks, and buses. In other cases, the sensors are counting bicycles. The number of which type of vehicle to count depends on local traffic patterns. In some cities, a significant number of commuters use something other than automobiles and mass transit. The key, in any case, is to capture the data that can be used to make travel more efficient. A similar approach may be implemented for other urban infrastructure such as lighting, utilities, and communications. Other IoT usage scenarios are in wind farms, pipelines, pumping stations, large factories, and elsewhere. Consider, for instance, a wind farm that consists of many turbines situated over large areas of land in a remote location. Each turbine undergoes varying acceleration, temperature, and vibration as wind speeds change. What's more, each turbine may have hundreds of sensors that capture this information. Collecting and analyzing this data enables real-time adjustment, such as changing the angle of the blades and altering other turbine operating parameters. That can up power production by 15% or more. And these changes are done in real time using IoT sensor data and analytics. Efficiency improvements are also possible for pipelines, pumping stations, factories, and elsewhere. Like wind farms, these applications tend to be dispersed over areas that may be found in remote locations. These applications, along with smart cities, have another characteristic in common. They benefit the most if there is a dense sensor network. In the case of traffic monitoring, instance, every possible path should have a sensor on it before and after every intersection, along with other sensors spaced periodically along the route. This is the only way to see not only how traffic flows, but also where vehicles are coming from and where they are going. What's more, since the traffic flow changes over time, the sensors must also capture and report the data often enough to paint a true picture of what's going on. In addition to sensor density, there also must be a wide variety of sensors. As a wind turbine, there may be many parameters that should be monitored. In the case of traffic, not only the number, but the types of vehicles may be critical for optimization. So, to make the IoT deployments, it is important to have a large sensor array as possible as a foundation. There also must be a mix of sensors so that the complete picture of the process being monitored can build up. So what are some of the barriers to implementing an IoT? A sensing network, of sufficient density and scope is, therefore, a first step to vital maximizing IoT benefits. However, deploying a proper sensing network is difficult due to 1. Complicated hardware and integration issues, 2. Varying equipment and diverse signal types, 3. Transmission and power supply cable challenges, 4. Harsh environments with small spaces for equipment, 5. Communication standards that are complex and hard to integrate, and 6. The need to cover wide areas cost effectively. Consider the first two items, complicated hardware integration issues, along with diverse equipment and signals. They are related. And that wide variety of sensors are likely needed. It may be necessary, for instance, to measure stress, strain, temperature, wind speed, and other parameters in an application. By necessity, collecting this data will typically mean that different sensors will be deployed, despite desire and efforts to avoid doing so. A wide variety of sensors often means that information will be carried on different signal types, with varying values and meanings for what the full-scale reading and what is minimal reading. All of this leads to complicated assortment of hardware and associated integration issues. This can be particularly difficult when many different sensor networks are being deployed, such as it's likely the case of smart cities and large factories. A smart city, for instance, could have sensors on every utility pole, water line, traffic light, and more. In the case of a manufacturing plant, which may have machines and tools from many different vendors, each machine or tool could be equipped with its own sensor. So the requirements of getting enough data, runs into some real-world challenges. That also is the case with the next two items that I want to discuss, putting cable in harsh environments in small spaces. Data generated by every sensor must be sent to some location for analytics and storage. If not done wirelessly, that means it must be transmitted by cable. There often may need to be run power cable as well if the sensor is not battery operated or does not employ a photovoltaic or other local source of power. Line cable can be difficult and expensive. The cost of putting down fiber optic cabling in urban areas can run into tens of thousands of dollars per mile in the U.S. alone. In the case of IoT sensing device arrays, any cabling must also often go into harsh environments where wide swings in temperature and humidity may take place, along with exposure to dust, vibration, and chemicals. A large food and beverage processing factory, for example, may be subject to periodic cleaning by soaps, chemicals, and water. In such industrial settings and other locations where an IoT sensing network is deployed, the available space for sensors may also be severely constrained, making installation of the sensor and cabling a challenge. And then the final set of barriers, communication standards, and the need to cover a wide area. The communication standards issue arises because there are a wide variety of sensors and consistently many different communication protocols. As in the case with hardware, This complexity in communication standards makes it difficult to integrate everything into a total and complete solution. As for wide area and long distance coverage equipment, there must be combined and distributed data transmission at a reasonable cost. Consequently, some frequently used wire solutions, Wi-Fi and cellular 3G, are not suitable. Any of these options would be able to support the data needed rates for which IoT device sizes may be only relatively low total number of bits per minute. However, existing Wi-Fi only works for short distances of a few tens of meters, less than 100 feet. Cellular connections typically have high data transmission rate fees, which rules them out. So what's an ideal solution? Well, what an ideal solution barriers look like, I think it should be, is highly flexible, provide wireless transmission, both Ethernet and low power wide area network, or LPWAN, integrate with the cloud, support standard communication protocols, be rugged with, for example, an IP65 grade protection against water and dust. Flexibility is important because we noted before, any solution that helps make deployment of an IoT sensing network easier must accommodate a wide variety of devices and types of sensors. This can be only accomplished when a solution can be configured to accept and work as many different sensors as possible. An IoT sensing network solution must work with many different devices on the input end of the sensor array. An ideal solution would also need to interface with a wide variety of devices and schemes on the output end as well. It is critical that an ideal solution have the right wireless transmission capabilities, which is where wireless Ethernet and WLPAN come from. The first has limited range, offers data rates, real-time transmission, and is standard in offices and some industrial settings. Despite its limited reach, wireless Ethernet may be the best choice for IoT sensing network in the right circumstances. However, LPWA has been designed for long-range communications at low bit rates and at low power consumption, which could be the case when deploying a network of battery-operated IoT sensing devices. The combination of transmission capabilities thus can cover situations inside many factories and those cases where sensors are located across a wide area and a long distance. Data rates will be higher in the former and lower in the latter. Importantly, the approach avoids the need to lay down cabling, an expensive, time-consuming affair, while still enabling extensive coverage required in many IoT usage scenarios. Cloud capabilities and standard communication protocols are necessary because they make integration of a solution easier. Cloud support means that any solution can be more easily incorporated into existing IT schemes, which will often already include cloud-based tools such as the ability to spin up, visualize data, and deploy an analytics package as needed. Having the right cloud capabilities will mean that incoming IoT data can be treated as any other big data problem. Support for standard communication protocols ensures the data generated by a sensing network can be gathered and disseminated as needed. The usage of standard communication protocol also means that the movement of data, which is critical, can be handled with minimal effort. More than that, a solution must be lightweight communication protocols designed for IoT use. MQTT, which is message queuing, telemetric transport, and REST, representational state transfer, are two examples of these protocols. Because such protocols provide the required information with minimal resources, they simplify, data transmission and ensure the vital information from sensors is readily accessible. As for being rugged, any IoT solution will, as mentioned before, be going into areas where conditions of high heat, humidity, dust, vibration, and cleaning by water washdown are possible. Thus, a solution needs to be available and to survive such an environment. An IP65 rating would mean the device enclosure would protect it against dust and low-pressure water jets from any direction. Offering such environmental ruggedness is why an ideal IoT solution should have an option, for such a rating. So in conclusion, The Internet of Things offers significant benefits and payback on what can be substantial investment. However, maximizing these benefits and return on investment requires that a dense sensor network be deployed. In return, this means that the sensor node solution must be wired, or should be wireless, flexible, rugged, and capable of providing with low power, wide area network deployed by many IoT devices. So, I hope that maybe gave you a little bit. If not, you gave you something to listen to on the way back from a hurricane. Anyway, I hope this went well, and I hope you listen to future other episodes. This has been Chatting with Chuck. I'm your host, Chuck. Look for me in the future. Take care.